Perfect.
Okay, so welcome to the second day of the workshop on phase transitions in particle physics. First speaker is Francesco Sannino on the future of composite operators. You have the screen.
Thanks a lot. First of all, let me thank for the organizer for inviting for this talk, and many apologies for not being there. But there is also teaching, which I have soon after this lecture, and there were several topics I would have loved to talk about, but I concentrated on one which I hope you will appreciate, which is mostly like how to use composite dynamics in a way which is going to be interesting for different audiences, and how to combine the efforts both from the lattice and from model builders to investigate different sectors of standard model physics. And I also want to say hi to all the colleagues and friends that I've seen in the audience and from which I've learned so much. But let me step back and go back to QCD. QCD is a theory of nature, features 3 colors and 6 flavors, at least one known so far. It's a theory which is weakly coupled in the ultraviolet and strongly coupled in the infrared. It also features spontaneous symmetry breaking in terms of the Cara symmetry, with a remnant in low energies in the form of quasi-custom boson. Now, the lattice has made tremendous progress about this theory. On the right-hand side, you see the running of the coupling constant. And this is actually from experiments, but also the alpha collaboration with fantastic progress on studying the evolution of this coupling. And there is no doubt that we see a running of the coupling that we don't know really what happens at very, very high energy because of the nature of the theory. We can only explore it in a limited range, but in this limited range, it definitely shows asymptotic freedom. How do you study this theory? However, well, this theory has been investigated in many ways, right? And here there is a little bit of upshot of the various models and methods that have been used to investigate this theory. At very, very, very large energies, we can employ perturbation theory. As the energy scale lowers, the theory becomes more and more strongly coupled, and we can only study corners of the strongly coupled dynamics in using, for example, effective field theories, and this, for example, the Cara-Lagrangian. If you want to describe, however, the spectrum of the theory and other properties, then we have to resort to lattice field theory or different limits, like a large number of colors, flavors, and quantum numbers. This can be, for example, large charge for investigating certain sectors of this theory, which are very popular at the moment, but I will not discuss those. If you're interested, you're welcome to ask. Sometimes this goes under the name also of semi-classical expansion. So I would say that the first 2 categories go under the name of faithful representations of QCD in certain limits, or strongly coupled dynamic in certain limits, which means that you make rigorous results. And sometimes you have to resort to less rigorous results and more in the model. That's why we call them models. And probably one of the most famous one is the quark model that basically started even before QCD. The Polyakov loop model, which in certain limits can be considered exact, and then Nambu-Lasinio or holographic string-inspired models. I'm sure I left something out here, but in practice, this is the toolbox we use to explore strong dynamics, not only in QCD, but even for theories which are non-QCD-like. In QCD or in QCD-like theories, we have several open issues. I'm sure that in this meeting, you will discuss many of them. On the left-hand side, you have my favorite diagram for trying to summarize the state of the art when it comes to the conformal window, which is, if you take SUN, and this is an SUN gauge tier, and you, for example, have 3 colors, then you actually can change the number of flavors, right? And you know that there is a point where you lose asymptotic freedom, and about this, you have to discuss whether or not the theory is a good theory in the ultraviolet. But below this, you actually have a well-defined theory, which has, let me plot here, which has a beta function like that, right? Beta function starts to be asymptotically free, and then we know that there is a Ben-Sachs fixed point, which means that is a perturbative infrared fixed point. And then as you move down, these fixed points move to the right, and eventually around this, we don't know exactly what happens. There are different scenarios one can imagine. One of the scenarios is that an ultraviolet fixed point emerges around this region here, and around this region, you actually have that the 2 fixed points emerge, and then below this, you have complex fixed points, and eventually a potential emergence of a dilaton. And this dynamic has been investigated still now, and has been investigated for quite a long time. The other windows here refer to different representations of the quarks. This is a 2-index antisymmetric, this is a 2-index symmetric, and then you have the adjoint representation. And there is really huge interest in this kind of physics, also because there are a lot of potential applications. And I will get back to the applications shortly. On the right-hand side, you have a different type of diagram. This diagram, on the other hand, takes, for example, QCD and increases the temperature or increase the baryon density. And this is it's a quark, and then, you know, what we can affirm without being wrong is that definitely you expect that here a very large, let me just use this, a very large matter density or temperature enter a quark-gluon plasma. We know what happens at very small baryon density at temperature, and eventually we would like to map the phase diagram as a function of temperature at density. Of course, these two diagrams are not completely disconnected, because effectively you could think of changing the number of flavors for QCD in this other direction, and you will have a more complex phase diagram. Many of you, I mean, from Maria Paola, which is one of the organizers, to Biagio Lucchini, to Marco Panero, you all basically, to Leonardo Giusti, you all been investigating many of these corners of the phase diagram of all these theories and making immense progress on all of this, right? So the community should really be thankful about the work you've been doing in the past several decades, I would say, by now. I learned personally very much from all of you, but the truth is that we can still do, and we should still do more, because it is actually required to go, I mean, in 2022, I think we should be able to do even more about these phase diagrams. They have immense relevance. For example, the finite density, finite temperature phase diagram is relevant for the understanding of the early universe, but you will see in a second, it's actually relevant also for new theories of beyond standard model physics. There are many open questions. So where does it end? The possible critical point, which is supposed to be a smooth phase transition. That this is a no phase transition, is basically a crossover. This is eventually a first order line. But again, truth to be told, I mean, we don't really have a clear understanding of this phase diagram for a number of technical issues, including, for example, on the lattice, adding the chemical potential given that the action is no longer real. So this summarizes for me, the interest in understanding more about strong dynamics. But let me just now do a top-down approach. What kind of composite dynamics we can have, right? So if you were to kind of summarize the type of strong dynamics we can have, and for a moment, just forget about the naturality issues. Right? I'm interested in the different type of strongly coupled theories we can have. You can follow me, right? Because I mean, it's hard to have a feedback since I don't really see you, but I imagine you've been able to follow so far, right? Yeah, I cannot hear you very well. But, are you following? I mean, I hear only somebody in the background.
Francesco, this was just background noise.
Okay.
So just go on.
Right, great, excellent. All right, so for the composite landscape, what can we do? I like this table because it summarized for me, you know, where I am in understanding these theories, which is, of course, much less than I wish I could know about it. But imagine you only have gluons, then you only have this type of interactions, which is a generalized Maxwell term. Then you have the representation that, of course, the adjoint representation for the glue. This theory is asymptotically free. Then to this theory, you can add the matter fields. For a moment, just let me consider vector-like matter field. And this is actually your kinetic term. And you can, at this point, be a little bit more daring and consider different representation, fundamental, adjoint, to index, and so forth, so on. The truth is that if you go to very high dimensional representation, you immediately lose asymptotic freedom roughly from the 3 index and above. So you keep it to the lower representation. You can turn the argument around and say, if you require asymptotic freedom, then eventually this is the reason why we've seen only fundamental and perhaps adjoint representations into index in the making of the fundamental interactions, because otherwise you lose asymptotic freedom. Of course, you can still ask whether the theory has an ultra-valid interacting fixed point. This is a very valid point. But this is actually the QCD-like dynamics. As I mentioned before, even this dynamics is not easy to address because it has a number of corners that have not been explored. Then you could replace a fermion with a scalar. There's nothing wrong from the composite dynamic point of view. At this point, you have actually interaction with scalars. This allows you immediately to add a new type of interactions, an accidental interaction, right? And that is the 5 to the 4th term. Here again, you can choose the representation. If you have super QCD, this is natural. This would be basically a squark, but it doesn't have to be supersymmetric. You can only add this term. And this is actually a very interesting theory because it allows also for being phi a scalar, not a fermion. You can avoid the Debye-Witten theorem, and therefore you can actually have color. You can even spontaneously break color. This theory in general has Landau poles, which means the theory typically is not well defined in ultraviolet because of this self-coupling here, and something else needs to do to make this theory well defined at short distances. Then, of course, you can go through a structure which is more similar to the standard model. So you have gauge interactions, fermions, and scalars. And as soon as you have scalars, in principle, you can also have new type of interactions beyond the self-coupling and the gauge coupling. You can also have Yukawa coupling. This is basically the making of the standard model. Effectively, that is the procedure we do to insert all these operators. And you can see that there are two accidental operators, so the self-coupling of the Higgs and the Yukawa coupling. And this type of Yukawa coupling clearly depends on the type of representations you have, both for the scalar and the fermions. These theories have been shown to, for example, be able to be free, safe, or in principle could also either be free or safe simultaneously, depending on what the different couplings do. If on the top of everything you superimpose also the supersymmetric relation between fermions, bosons, and gauge degrees of freedom, then you can have also SUSY compositeness, which is very interesting. And I remind you of the wonderful work by Seiberg, right? About the conformal window of n equal to 1 super Emils, which allows you to exactly pin down the lower boundary of these conformal windows because of the supersymmetric, power supersymmetry. Good. All right. So this was the landscape that we could imagine about strongly coupled theory. So what can we use them for? Imagine that you had solved for these theories and you knew their dynamics. What can you do? Well, okay, so obviously we can understand QCD. QCD is important for collider physics. For example, HC is I could say is a QCD machine because it's proton-proton collider. You can and many of the limitations that comes from the QCD from the LHC, it comes from QCD backgrounds, both in the hadronic final states, but also in the production mechanisms. Then you could understand better the physics of the early universe. And last but not least, if you look at extended compact objects in the sky, well, neutron stars are compact stars for which we know very little about their internal structure, and mostly because we have to rely on models. For example, we can't really be sure whether we can have compact stars featuring a quark core. This is from the bright side. On the dark side, well, we still have a strong CP problem. And do we have axions? And how do we solve that? Of course, you know that QCD can be augmented by a topological term. This topological term has a coefficient, which is an angle. And when combined with the physics of the mass of the quarks, we know that this angle is insanely constrained by the electric dipole moment of the neutron. And one way out is to upgrade the angle to be, way out of this issue is to upgrade the angle to be the vacuum expectation value of a new field, the axion. Okay, and there is a lot of axion-like physics on the archive right now. I mean, many of these models are just simply Gaussian-like states, but that's why they call ALPS, which means axion-like particles, which are supposed to be light. If you have string theory, you have tons of axions coming from string theory. None of them seems to be able to solve the QCD problem, though. Anyway, moving on. So this is just the QCD physics. I'm sure there are other applications that I missed. About new composite dynamics. Well, okay, so QCD could be an analog computer for some new type of dynamics. And once you have this new type of dynamics, let me start from the dark side. Well, what can you do? Well, you can have dark matter made by dark baryons. You can have dark matter made by dark pions. You can have Simpson-like particles. These are not the Simpson, not short for Simpson in the cartoons, but stands for strongly interacting massive particles, where they have this, you can construct models, which can be fun, where the dark matter relative density does not come by equilibrating with the standard model plasma like the WIMPs, but instead you have so-called number changing operators. So for example, you can have pi pi into pi pi pi. So let me ask you, I mean, do you know how to do this? I mean, can you imagine how to do this in a strongly coupled theory? And I'm just checking if you're awake, so if you got enough good coffees in Firenze. But one way to do this is, for example, if you have, give an example, if you have an SU2, with 2 is the number of colors, Now, if you have an SU2 theory and you have two direct flavors, you have an SU4 global symmetry that through the condensate of the Fermi condensate breaks to symplectic as before. And you have a topological term, a Wetzel-Witten term, that indeed is made by alpha to the fifth integral in this is the boundary of topology of the five-dimensional world, d phi x, and alpha is u minus 1 du, with the u is the pion Lagrangian. Sorry, the pion is e to the I pi. So because of that, you can show that this operator leads to number changing interactions. And these are number changing interactions, indeed pi pi, that goes into pi pi pi. So you can generate the dark matter through this interaction. And now, because it's an endothermic reaction, this is basically heat up your medium. So it's like having a cup of coffee that heats itself, and then you have to blow over this cup of coffee to cool it down, and you blow it with standard model interactions. So that is the mechanism behind, for example, the simp. Okay, you can even have inflation through composite dynamics. However, to have inflation from composite dynamics, you have to require no minimal coupling to gravity. All right, this was a little bit of summary for what you can do on the dark side. On the bright side, the new composite dynamics, well, I mean, I cannot avoid talking about Technicolor because, you know, it's one of the probably most elegant solution to the naturality problem, most minimal too, that one could have thought of for the extending the standard model and making the standard model Higgs sector natural. A variant of this that has been quite popular in the literature is that what if the Higgs, rather than being you know, the sigma, or if you want the linear, the QQ bar condensate is actually a Gaussian boson per se, right? I would call still this is a variation of the technical dynamics, but because of the history, has been given the name of composite Gaussian Higgs. And then again, depending on your taste for naturality, you can imagine to add the scalar particles again, and then the scalar particles can either be seen as composite of some unknown fermionic dynamics, or once you put it in from the get-go, you're able to write models which are renormalizable or well-defined up to the gravity scale, and they can give mass to the standard model fermions in a simple way. These models can address, I don't know if I will have the time to arrive to this, but can address the current flavor anomalies in the G-2 of the muon, which, as you know, are taking a good space of the archive because we love to have new physics. And if you want to know more about that, feel free to ask. I think it's quite an interesting, relevant topic. Many of the things that I said are summarized in the physics report, which I wrote with Giacomo and Claudio. In this, you will also have a sufficiently up-to-date review of the conformal window and dynamics on and off the lattice. Okay, so this summarizes the, for me, the interest in investigating strongly coupled theory. Now, I want to give few examples on what can we do with this new strongly coupled theory. Can be fun, what can we learn? And let's see. So let me start very simple, okay? And how simple can I start? Well, I can start by just saying, well, what if, together with the standard model, I introduce a new dark glue sector, which only couples gravitationally with the standard model. So effectively, this is the simplest thing you can possibly imagine. So a dark sector which only contains glue. You'll admit that this is really the minimalist thing I can possibly do. To our surprise, this was not done professionally. Okay. So imagine you have a dark sector made only of pure glue that cap only gravitation to the standard model. So what is the Lagrangian? Okay. Lagrangian is Lagrangian of the standard model plus a new glue sector. You could also imagine some potential residual interaction. This can come from gravity itself, quantum gravity, but can also come from particle physics. But we will neglect at the moment. So why is it dark? Well, it's pretty clear why it's dark, because it interacts with the standard model very minimally. So how do we know that there is this sector? Well, I mean, at the very least, interact gravitationally, as we say, that this is the minimum interaction with gravity. Okay. So this is the standard Einstein term, and then the rest is you get it by generalizing with the interaction with gravity. So let's go back to the pure glue fast. And here I feel very much at home because the people in the audience have worked on that and they can teach me so much about that. So please don't switch off your brain on that, because it's just a little summary for then see how this is relevant in cosmology. Okay. So let's concentrate on a pure SUN theory. Okay. In a pure SUN theory, there are no global symmetries, except for the center of the group symmetry, which happen to be a discrete group Zn. And it has this nice property that at finite temperature, Zn is broken at high temperature, is restored at low temperature. Okay. So, and it effectively works as a way to consolidate our understanding of confinement. At very high temperature, you have free gluons. At very low temperature, you have a glue ball theory. Lambda is some confining scale, which also reflected it in some temperature for confinement or deconfinement. Okay. Good. So this is a very good way to transcribe confinement into a symmetry property. Once you have a symmetry, you can then define an order parameter. The logical choice for the order parameter is what's known as the Polyakov loop, which is nothing but a Wilson line in the temporal direction. And mathematically, you write it as the path integral of the exponential of, this path ordered in time. And this is actually your temporal component of your gauge field integrated in time. And now if you take the trace, because this is a matrix and this is the simplest possible Polyakov loop you can construct. You can construct a Polyakov loop of different symmetries, but this is actually under the gauge group, but this is actually the simplest one. Now, if I plot L as a function of temperature, right? Then you see that at small temperature it's 0 and high temperature is 1. Is exactly 1. Okay. Now for the SU2 gauge theory, I mean to SU2 glue ball, it's a second order. This is really in the same universality class of Ising. However, for any n larger than 2, you actually expect this to be a first order phase transition. So there's a first order jump around the critical temperature. So this you can now write in effective theory. I believe Rob was one of the first to come up with this, and 1 year later I actually also worked on that and write down the effective theory. What the difference between Rob's work and my work is that I actually showed how to the information of the mathematical object, which was a Polyakov loop, can be transferred to the physical degrees of freedom, like glue balls, right? Because there was an issue when Rob came up about this. Some people were saying, but it's a very mathematical object. How do I actually see it in real life? And you can show that you can write down an effective action that contains glue balls and Polyakov loops in a coordinated way, so where the information of the Polyakov loop gets transferred to the physical degrees of freedom, in this case, the glue balls. In real life, you will only see physical objects, right? You don't see a Polyakov loop, so you have to reconstruct the Polyakov loop action out of physical quantities. All right, good. So how this transcribe into the dark evolution of the dark glue evolution in cosmology? Okay, assuming that now n is larger than 2, so it is reasonable now to assume that this is a first order phase transition. And now the time, as you know, moves in this direction, which means at the very short times we were at a very high temperature, and therefore we had a deconfined medium. Around the critical confinement, if you want, scale, you start creating bubbles of the right vacuum. Okay, so the right vacuum is inside these bubbles, and eventually they start expanding at the speed of light, and they will find each other, and they will live in the some gravitational waves when they collide. And we finally, after this phase, enter the confined medium, where all the bubbles are basically coalesced in the new medium. So what we would like to do is to see if there is any remnant of this primordial time where the gravitational waves can be detected, and tell us anything about whether or not, besides the ordinary bright side evolution, there is this dark side. And this is the only way, once you have such a tiny interaction with the standard model, to see if there is any relic of this world projected onto us. And we can hear that. Now, not a bene, that this scale is arbitrary. The scale of confinement is not, it's God-given, right? This one we can choose. We cannot choose SUN. I mean, we can choose the SUN gauge group and the scale of confinement, because that's not given by the SUN gauge theory, but only by experiments. So this, in fact, is a free parameter of the theory. If there are no further questions, if there are no questions, so far, let me go a little bit beyond and see what is been our strategy to investigate for arbitrary SUN this model. Okay, so this is a flowchart of our computations. These were done in collaboration with Manuel Reichert, Wang, and then later also with Chen, when we actually looked at the effects coming also from the fermions. Okay, so we went back to the papers of Biagio and also from Marco, and big thank also to Marco that answers some of our questions. So you go back to the lattice simulation of SUN gauge theories. And from this, we then applied two potential strategies to be able to arrive to the gravitational wave spectrum. Okay, one strategy was to get from the lattice simulation the latent heat into surface tension, then write down a thin wall approximation to calculate the Sphaleron processes. From a direct computation, determine the nucleation rate. And this allowed us to get then the gravitational parameters, alpha, beta, and the velocity of the wave velocity of the bubbles, and finally get the gravitational wave spectrum. There's another way to do that, is to determine the energy momentum tensor pressure that in some cases was given in the lattice. From this, to reconstruct the Polyakov loop model, because you are able then to get the coefficients of the model. And here we went beyond the state of the art, because it was actually not done for 4, 5, 6, and 8 flavors, and then generalized for arbitrary n. do then a chi-square fitting via Markov chain Monte Carlo, and eventually calculate the same quantities again. So when we felt that these were very much in agreement with each other, we felt confident that we had an understanding of the gravitational wave spectrum. So to make the story short, we were able then to calculate this alpha, which is linked to the phase transition strength. And alpha is, can be calculated to be 1/3 of the difference in between the two phases of the stress energy tensor, divided by the enthalpy density. Can you still, you can still hear me, right?
Yes.
All right, very good. So the omega plus is what's called the enthalpy density. Plus means outside the metastable of the bubble, and minus means inside the bubble. Then there is another parameter, which is the Hubble time, and which is in units of the Hubble time, and measure the inverse duration of the phase transition. This parameter, we find out that for generic strong coupled dynamics, is always quite large, effectively making smaller the signal, unfortunately. The other thing we observed that the sound waves are the one responsible mostly for the gravitational wave spectrum rather than the collision, other bubble collisions because of the turbulence effects. And we also observed that the maximum of the signal came for n around 6, but there was quite an independence for any number of color larger than 6. All and behold, these are the gravitational wave spectrum as a function of the frequency. Now, these three curves corresponds to different energy range for the confining scale. So the blue means around the JEV, then the orange around the TEV, and the yellow around the beta electron volt. You see that we have put here the future experiments, and effectively only the SIGO and BBO have a chance to be able to detect these gravitational waves, which means is that, you know, the dark side can be extremely rich, and we won't be able to say much about that for a very, very, very long time. Now, trying to be a bit more optimistic, this is for BBO and for the SIGO, the signal to noise ratio in terms of the deconfinement or confinement temperature. So this is, as I told you, is the free parameter because we don't know in the dark sector where is the confining scale. And you see that in principle, you're able to detect that in the hundreds of JEV region. This is kind of a coincidence that depends on the type of experiments that you want to detect, you want to use. Okay. You can also imagine that in the dark sector there are n copies. I mean, once I saw the graph in figure 12, I mean, I thought, okay, no, we thought maybe we can boost this by increasing the number of copies in the dark sector. Unfortunately, this does not help very much because it's true that you can increase the number of copies, but you cannot increase the energy density in the dark sector too much because they still contribute to the energy density of the entire universe. So effectively, you have more copies, but you have to share it across these copies. Nevertheless, I mean, you could get a little bit more, up to 3 copies, more signal.
Francesco?
Yeah.
5 minutes left.
Very good. I'm actually almost there. So you can generalize this, and that's what we did in a very recent paper. You say, okay, now that we have built our experience about gluon dynamics, now let's add also matter fields, fermions, still minimally coupled to gravity. Things get clearly quite seriously more complicated because, as you know, now in principle we have 2 phase transition: the Carrier phase transition and the deconfinement phase transition. For the Carrier phase transition, you have the quark condensate. For the confinement, you still have the Polyakov loop. However, the confinement phase transition, the existence depends on whether the fermions respect the central symmetry or not. So what does that mean? Well, on the left-hand side, you have you have a plot where I show the order parameter for the carrier condensate and the order parameter for the Polyakov loop. Now you see that in the absence of quark masses, the side-by-side condensate is indeed an order parameter. It goes to 0 at high energy, and it goes to a number at low energy. However, the Polyakov loop, in the case of, for example, fundamental representation, goes to 1 at high energy, but then it goes to a number which is different from 0 at low energy. The reason for this is that in the fundamental representation, if you try to take two heavy quarks and pull them apart, you can break the chromomagnetic string by introducing light quarks, and that actually makes the Polyakov loop not an order parameter. If you want, it breaks the center symmetry. If you, on the other hand, use a joint representation for the quarks, then you can show that you can never break the string, and therefore the Polyakov loop is still an order parameter, like the condensate. The two scales for confinement and confined don't need to be the same. One more thing I want to add, that does not mean that you might not have a jump in the Polyakov loop. So you can still have basically a jump, but it's going to be a crossover. So we played with the different examples. I'll just give you the results. So 3 Dirac flavors in the fundamental of SU3, which very much looks like UCD. 1 Dirac flavor in the adjoint of SU3, and this, I guess, Biagio is going to get excited about that. 1 Dirac flavor in the 2-index symmetric of SU3. Our results were that for the 2-index, we saw a stronger confinement phase transition. We used a model computation, the Polyakov number Ionarzinho, to estimate this phase transition. And therefore, we could actually say that in principle, you could look at the confinement phase transition with BBO with a signal to noise ratio over the time. And this is the actual results. So you have BBO, right? So, and again, it's actually a little bump with, again, sound waves are more important than turbulence. And on the right-hand side, you again have the BBO standing out, and the green is indeed 3-color, 2-index symmetric representation with 1 Dirac flavor. Indeed, the quasi-confinement phase transition has higher chances to be observed. Okay, so in the last 2 minutes, what would be great to have, right? So for the pure glue, we relied on both lattice results and the computations by a Polyakov loop and the T-mole approximation. I believe much better can be done if we get the better thermodynamics for different SUM from the lattice. In particular, it's very interesting to get the string tension and the dependence on the number of colors in a better way. Gauge fermion thermodynamics, we know it's very hard, but it would be great to be able to reconstruct the carrier phase transition, the Polyakov loop phase transitions in a bit more accurate way. I remind you that for BSM, we don't need precision of the order of the percent, but I mean 5 to 10%, that would be great. This also tells us that it would be nice to kind of consolidate the understanding of the carrier phase transition and the confinement phase transition for different representations. One thing that I went very fast is that to calculate this alpha parameter, which is a strength of phase transition, we also need a back constant, which can be estimated in a few cases from the lattice, otherwise it's not known. And then I would love to be able to extend this to near conformal dynamics, because I expected that in this case, the phase transitions might be actually even stronger. So this is the future wish list, and again, it still contains the conformal window, the temperature density phase diagram. how do we can go beyond perturbation theory, and there are, for example, now semi-classical methods that have been employed, and I did not discuss here, but I can tell you are very promising. And eventually there is a possibility to discover composite dynamics either in the bright sector, for example, if RK and RK star and G-2 and or G-2 are validated by experiments or perhaps by gravitational waves. So with this, I finish, and I think more or less on time. And I thank you for your attention.
Yeah, thank you very much, Francesco. Really nice overview to the composite dynamics. Questions, comments? Elena? Oh, yes. Sorry.
Yeah, thank you very much for excellent review. I have a naive question. What about the role to composite dynamics of other dark matter candidates, like, for example, dark photons which couple in electromagnetic way by U1, U1 prime symmetry breaking? Are they important, or what's their role in your consideration? Thank you.
Yeah, no, I mean, thank you for asking this. I mean, I concentrate on one simple example to show how little do we know about these things. Yeah, dark atoms, I mean, absolutely, they're very, very interesting. And there, for example, you can ask many questions, because if you have dark atoms, often happens, even with the QED, that you have Landau poles which are very, very close. And that's are typically ignored in the dark matter community, very, very, you know, close to the electroweak, but even a much lower scales Landau poles. There eventually you have to also enter the realm of strongly coupled theories, in particular, even QED, and how to solve that. So there will be corrections to that, will be also correction to the bound states there, and we know very little about that, and I think that can be studied. That it can be studied typically a large number of flavors, so where you can actually have the older, you have the beta function of QED, the infinite number of flavors, so you have it known, a leading order 1 over NF and 1 over NF square. That also, there's a lot of progress there. Also, we know better the structural singularity there via the resurgence. But yes, but also for the SIMP, so-called miracle or non-miracle, there is still a lot to be done for the SU2, for the symplectic, I mean, the, let's say, two-color QCD, which many people in the audience have been working right on. So for that, there is still a lot that can be done. And so I think there are, maybe one thing is missing in this field is a little bit of a white paper on the priorities and what has to be done first for standard model and beyond in non-perturbative dynamics. So I don't know if this helps, but I think one could sit down and see what are the things that can be done in 5 years, 10 years. Many of the things I talked about, there are people in the audience that can do very quickly or quickly enough. So I think it would be nice to do that. I don't know if this answers your question.
Hi, Francesco, it's Biagio here. Thank you very much for the nice overview. I wanted to ask, what are, in your opinion, the quantities that the lattice should be focusing on? You have talked about critical temperature, order of phase transition, Polyakov loop. Any particular other observable of finite temperature, like latent heat or other particular susceptibility, specific heat, etc.?
Yeah, let me just go back to this little flow chart here. I mean, you can see here, what is needed. So basically, if you can, latent heat, surface tension, energy, momentum, tensor, pressure, these are in principle even the entropy. These are the 5 things that are most wanted for cosmology. So, but in general, they're needed. Okay, so I don't think that is. And this actually things that in your toolbox, especially for the SUN gauge theories, you have from what I know from your work, amazing work. So this would be very nice. And and try to kind of, because once you have this, then just for the pure glue, then we can build on this to also with the fermions. And we know it changes, but we also know that, you know, we have to start from the pure glue. So these are the things I will concentrate first.
Okay, thank you.
Yeah.
Uwe, there was a question in the Zoom room. Please start.
Yes. Yeah, hi, Francesco. Thanks for the interesting talk. I have a remark about the pure glue scenario. Namely, if you go to the deconfined phase, if you have a non-trivial center, you also have deconfined domain walls, yes. Unless you think that inflation has wiped them all out. But if you have them, then there is actually another way to go through the phase transition, which is called complete wetting. And this proceeds like this. You have a domain wall that separates two distinct deconfined phases. And this is sort of a natural seed for the confined phase to show up as a complete wetting layer, like the liquid of tears in our eyes and stuff like that from condensed matter. And so this would also be interesting to think about, perhaps. And
oh, absolutely. If you, actually, this is very nice. So you call it wetting layer.
Yeah, so we have a couple of papers from ancient times about this stuff.
So apologies for not.
No, don't worry about it. I'm just saying that the phase transition has other aspects.
That would be, in fact, I mean, this is very interesting because, I mean, it's very important too, because it might actually increase the strength of the phase transition, actually. So
yeah, I mean, it's sort of dangerous. If you have domain walls, they might overclose the universe. And yes. Another comment, a simple way to get rid of this, if you would not like it, is to use a gauge group without a center or with a trivial center. For example, the exceptional group G2, then you can be sure there is a first order phase transition, which Michele and Pepe and I worked on a long time ago. And then you have your scenario without any other admixtures of this wetting dynamics.
Yeah, no, I mean, as I said, it's one of the, we try to do kind of systematically, starting with the SUN. We started to do it systematically with the SUN, but I mean, clearly it's nice also to look at the G2. So this is the one I remember well, is the one, and I worked on that, but for the conformal wind. So this is the one where you have basically, indeed, there is no order parameter for it, but there is still a first order phase transition, right? So this is the G2 kind of.
So, okay, I think we have to close. So let's thank Francesco again for this.
Thank you all of you.